Hello science enthusiasts. Welcome again to your favorite science show, Be Convinced Science. In the previous video, we have discussed about carbonyl chemistry and we have discussed about how nucleophilic addition take place in the carbonyl compounds. Now, in this video, we are going to discuss more about the carbonyl chemistry and this time we will discuss about the nucleophilic substitution to the carbonyl chemistry. In this video, we will learn what is the difference between the nucleophilic addition to the carbonyl and the nucleophilic substitution to the carbonyl group. If you have not watched my previous video, I would suggest you to watch that video after this video. In that video, I have explained the attack of nucleophile on carbon of the carbonyl group, and that attack is only possible because of the electronegativity difference between the carbon and the oxygen atom of the carbonyl group, which encourages the partial electron shift of pi bond towards the oxygen atom. That creates the partial positive charge over carbon atom, and this charge attracts the electron rich nucleophile to attack over it. This nucleophilic attack converts the pi bond between C double bond O into a single bond CO minus and converts the sp2 hybrid carbon into sp3 hybridized carbon atom. Now as we can see, a new group, that is nucleophile, is attached to the molecule and it forms the new carbon-carbon bond, which is why it is a nucleophilic addition. Now imagine if we add nucleophile to the carbonyl group, and this time instead of conversion of C double bond O to C single bond O, some group which is attached with the carbonyl carbon leaves the molecule and the attacking nucleophile take the position of the leaving group. Then we will call this as a nucleophilic substitution reaction. In this video, our focus will be on explaining how the nucleophilic attack at the carbonyl carbon followed by the loss of the leaving group happens. Then we will discuss what makes a leaving group a good leaving group. Further, we will discuss the tetrahedral intermediate state. In this journey, we will also learn some of the very important conversions that are very important for competitive exams and interview perspective. This is the second part of the carbonyl series. I'll bring the third part of the carbonyl series soon after this video. So if you haven't subscribed yet, subscribe our channel. Because in this channel, knowledge is for everyone and it is free. We have discussed that when an alcohol attacks the aldehyde or ketone, the product form is hemiacetal. But this reaction is reversible, which means the product is unstable and reverts back to the starting carbonyl group. The instability of this reaction is because of OR group, as this group can be easily expelled from the molecule. Such group that can easily leave the molecule by taking with them a negative charge are termed as leaving group. So we have to keep in mind that leaving groups are anion such as OR minus, Cl minus, Br minus, RCOO minus, etc. that can be expelled from the molecules taking their negative charge from them. If the attacking nucleophile is also a leaving group, then there is a high chance that the carbonyl reaction will be reversible. But what if there is a race between the leaving group to prove who is the better leaving group? Then in that case, the one who is a good leaving group will leave the molecule and the other one will stay in the molecule as a substituent. Before understanding how to identify which is better leaving group during the reaction, let's just revisit the Grignard reaction, but this time not with aldehyde or ketone, but this time with ester or acid halide. We have seen that when organometallic Grignard reagent attacks the aldehyde and ketone, it gives alcohol and the new CC bond. But when the Grignard reagent attacks the ester group, first it forms the unstable intermediate state, followed by the loss of OR minus as a leaving group, and this time the product is not alcohol but it is a ketone with a new CC bond. So we can see here that aldehyde and ketone gives nucleophilic addition, while carboxylic acid, ester and acid halides give nucleophilic substitution reaction. This ketone product can further react with the other molecule of the Grignard reagent to give a tertiary alcohol. To understand why this change is observed in the case of ester, in comparison to the aldehyde or ketone, we have to closely look into the mechanism of the reaction when the alkyl group from Grignard reagent attacks the carbonyl carbon of the ester. The intermediate state is formed with O- group, and we call this state as tetrahedral intermediate state. Here O- is not stable. It has two possibilities. Either it gain some H plus species from the reaction mixture, or it reverse back to form a double bond C double bond O. Since the presence of leaving group OR in the molecule, which facilitates the reformation of the double bond more easily by leaving the molecule and providing stability to the molecule, hence the molecule chooses the stability. But I have a question. Why this tetrahedral state is unstable? The answer is the leaving group, which makes it unstable. If any group leaves the molecule, the product form will be the substitution and the product will be sp2 hybridized carbon. Now coming back to the question of how we will decide whether the group attached to the carbonyl is a leaving group or not. For this, let's take an example. When the ethanol attacks this acid chloride, first it will form the unstable tetrahedral state. After this, you can see here Cl- is leaving out from the molecule and the product forming is ester. But why the Cl- left the molecule? The answer is it can form a stable anion after leaving the molecule. If the leaving group can accommodate the negative charge over it and can remain stable and quite unreactive, then it can be a good leaving group. Let's understand it in a different way. So, in an unstable tetrahedral state, there are three choices for the leaving group. Out of them, Cl is the best leaving group because it is most stable in the anionic form. Also, the leaving group ability is directly related to the pK value of the conjugate acid of the leaving group, which means stronger the conjugate acid will show a better leaving group ability. Cl minus conjugate acid is HCl, which is very strong and having pK value less than 0, while ETO minus having a conjugate acid ETOH, which is ethanol, whose pK value is about 15, which is not much good in compared to HCl. And if we look into the methyl minus conjugate acid, it will form methane, which is having very high pK value about 40. So it is a worst leaving group. In nutshell, if the leaving group can make a strong acid on combining with H+, then that leaving group is a good leaving group. Take another example. Suppose this time the amine nucleophile attack to the acid chloride. The product will be amide. Because in intermediate state, the leaving group choices are Cl- and NH2-, out of which Cl- conjugate acid is HCl, while NH2 conjugate acid will be amine, NH3, which is basic. Hence, very high pK value about 25. Let's take one more example to make it more clear on leaving group ability. This time take ester. Now if amine attack to the ester, what will be the product? The answer is amide, because the conjugate acid of OMe- is MEOH, which is methanol, which is more acidic than the NH3 amine. So leaving group will be the OMe-. These type of nucleophilic substitution not only depends upon the leaving group but also it depends upon the two other factors. One is the good electrophilic carbonyl molecule and the other is a good enough nucleophile. To understand this, let's just reverse the example which we have taken just now. If we try to react amide with alcohol, the reaction will not proceed because in amide the carbonyl group is not much electrophile. The alcohol is not enough nucleophile to react with the amide carbon. In amide, the nitrogen atom attached to the carbon of the carbonyl group provides the lone pair of electron for conjugation, which results into the formation of the 2 resonance structure. And because of this conjugation, the carbon of the carbonyl doesn't feel the electron deficiency, and hence it is not much electrophilic in nature. In case of ester, also this type of conjugation exists, but the oxygen molecule in ester is more electronegative compared to nitrogen. So oxygen pulls electron more towards itself which creates electron density deficiency in case of ester. To increase the reactivity of these types of reaction, we have to add catalytic amount of acid in these reactions. Because the proton of the acids, for example HCl, can protonate the carbonyl oxygen, which imposes the positive charge over oxygen atom. To compensate that positive charge, oxygen atoms start attracting more pi electron towards itself, eventually generating more electropositive carbonyl carbon, which is good for reaction. Now here is the catch. The acid catalyzation in these type of reaction not only increase the electrophilicity of the carbonyl carbon, they can also make the bad leaving group into good leaving groups. Let's understand this with an example. Suppose alcohol attacks to the acid. It will generate two leaving group possibilities, either OH minus or the reverse of the reaction by removing the attached alcohol. Although this reaction is reversible, both the OH minus and OR minus are leaving groups. But if the acid will be available in the reaction mixture, then it will protonate the leaving group OH to convert it into H2O, which will leave the molecule to form a stable ester as a substituted product. Moving on with the same concept, suppose if we want to make acid from ester, then the very famous hydrolysis reaction can be done for this conversion. For this reaction, we need a water and some catalytic amount of HCl or H2SO4. But this reaction is reversible and gives very low yield. If you want to achieve good yield in hydrolysis, then little change is required in this reaction. If we react ester with a base having OH like NaOH or LiOH in water and heat it around 100 degrees Celsius, you will get about 90% yield. Let's understand how this base helps in this reaction. The base will provide the OH minus as a nucleophile, which is much more powerful nucleophile in compared to H2O. So this OH minus attack to the carbonyl carbon and the presence of good leaving group OR minus will leave the molecule and the final product will be the COO minus salt, which can be protonated to form COOH acid. Interestingly, the soap also traditionally made by hydrolysis of ester obtained from oils. Not only ester, but amide can also hydrolyze to give COOH under acidic or basic condition. But the conversion of amide to acid is not that easy. As we have discussed, the carbonyl group of amide is not much electrophilic because of the delocalization of nitrogen lone pair and creating a resonance structure which increase the electron density over carbon of the carbonyl group. Also, NH2 minus is not a good leaving group. To convert amide to carboxylic acid, it has to remove NH2 minus group from it. Let's understand how hydrolysis of amide happens. Hydrolysis of amide happens under basic or acidic vigorous condition. This amide to carboxylic acid can be done by acidic condition. In acidic condition, the carbonyl oxygen will get protonate and not the nitrogen of amide, because when protonation happens to the oxygen atom, then the lone pair of nitrogen will delocalize to form two resonating structure. While if the nitrogen atom get protonate, no resonance structure will be possible. Okay, now after understanding the protonation of the amide group, the CO carbon become more electron deficient and hence electrophilicity will be increased in the amide. To this electrophilic carbon, water molecule can attack to form tetrahedral intermediate state. In this tetrahedral state, the nitrogen atom will gain the H plus from the acidic environment of the reaction, which will make the RNH2 as a good leaving group. Once the protonation complete, the amine species will leave as a neutral stable molecule from the tetrahedral state. Hydrolysis of amide can be done in basic condition as well, when a hot solution of sodium or potassium tertiary butoxide in high equivalence is used. Now in the last section of the video, which is very important, we will discuss some of the possible conversions that can be done with carbonyl nucleophilic substitution reaction. To understand the conversion, we need to keep two things in mind, which we have already discussed for these type of reaction. First is the nucleophile, how strong or mild nucleophile we are going to use for particular reaction, and the other is the reactivity of the electrophilic carbonyl carbon. Check this chart. We can see the most reactive carbonyl carbon for nucleophilic substitution is acyl chloride, because in acyl chloride the carbon of the carbonyl is most electrophilic. The chlorine atom next to carbon pulls the electron density towards itself because chlorine atom is electronegative. Also, the lone pair of the chlorine is not enough well delocalized in acetyl chloride due to difference in the orbital size of chlorine and carbon. Next in reactivity series, anhydride. This group is more reactive because the oxygen atom lone pair is delocalized with two different carbonyl carbon. Hence the carbon is comparatively less electron density. After that, ester reactivity, which is low because of oxygen atom lone pair, well delocalized, which increases the electron density over carbon, and the least reactive carboxylic acid derivative is amide, in which delocalization is maximum and the electronegativity difference is less. So now, as we know, the most reactive amongst all the carboxylic acid derivative is acyl chloride. If you want to do any conversion with carboxylic acid, like for example conversion of carboxylic acid to ketone or ester or even amide, the best strategy is to convert carboxylic acid to acid chloride, which is now very reactive and can be easily react to give various products. The conversion of carboxylic acid to acyl chloride can be done by adding SOCl2, POCl3 or PCl5 to the carboxylic acid. Take carboxylic acid in a RB, fill the RB with inert gas like nitrogen or argon. Now to that RB add your carboxylic acid, whichever you want to convert. Then add SOCl2 liquid and the base like triethylamine or DMAP. Stir the reaction at 80 to 100 degrees Celsius for 2 to 3 hours and the conversion will happen. So far in this video, we have learned so many things about carbonyl chemistry and also the nucleophilic substitution to the carbonyl group. I know you might have many questions regarding this topic in your mind, and that is good because science teaches us to question and to learn. If you have questions regarding this topic, feel free to ask in the comment section. Also, you can DM me on my Instagram ID. The ID is Beacon Bin Science. You can check it in the comment section. I will ping it there. Thank you for watching till the end. See you in the next video.